So we'll have time afterwards for questions, but if you do have any questions during this presentation, you're welcome to ask them as well. So we are made of star stuff. Some of you may recognize this famous quote. It's from the astronomer Carl Sagan. In this quote, he was summarizing the fact that many of the elements in our bodies originated in the centers of stars billions of years ago. And tonight we're going to take a closer look at those origins of the elements. Now, to begin to explore the origins of the elements, we need to examine a few pieces of physics related to atoms. And the first question we need to answer is, what is temperature? What does temperature mean? So, for instance, if I say that air in this room is cold, what does that actually mean? Well, temperature refers to the energy of motion or the kinetic energy of atoms. So, for instance, if the air in this room is cold, that means the atoms are moving around slowly. They have a small energy of motion. But if the air is hot, that means the atoms are moving very rapidly. They have very high velocities. And we'll see how this is relevant to the origins of the elements in a few moments. So the second issue concerning the physics of atoms that we need to address is what makes one element different from another element? And the answer is that the element is identified, is distinguished based on the number of protons in its nucleus. So for instance, the hydrogen atom has one proton, the helium atom has two protons, lithium has three, and so on. And so different elements have different numbers of protons in the nuclei. Now you might think that, well, maybe we can make elements by combining small light elements into heavier ones. For instance, maybe we could combine a lot of hydrogen to make very heavy elements. But there's an obstacle to doing this. And that's the repulsive charge, the repulsive force due to the positive charges of these protons. So these two protons both have the same charge, and so they want to repel each other rather than attract. Now, if these protons have a low temperature and low velocities, then they won't get very close to each other before repelling. But if the temperature is much higher, and they're moving much more rapidly, then they might be moving rapidly enough to overcome the repulsion. And if they can actually come close enough to each other that they physically touch each other, then they'll stick and fuse together into a heavier element. And so if we want to fuse an element, fuse the lighter elements into heavier elements, we need to achieve a certain minimum temperature to do that. Now, as we just saw a moment ago, different elements have different numbers of protons. And elements with more protons in their nuclei, because they're more charged, more positive charge, they're naturally going to have a greater barrier to fusion. So at a given temperature, the hydrogen might fuse together, but the velocity of the atoms won't be fast enough for heavier elements like helium or lithium to fuse. And so in order to overcome the greater barrier due to repulsion in the heavier elements, we need to reach a higher temperature to fuse heavier elements. So for hydrogen, we can do this at a temperature of about 10 million Kelvin, but for heavier elements, we need to reach higher temperatures to fuse them and to make heavier elements out of it. So when and where were the elements created in our universe then? Well, we start off with the Big Bang, the huge explosion that gave birth to the universe billions of years ago. At the moment of the Big Bang, the universe is full of radiation, it was full of light. And then in a split second, much of this radiation transformed into protons, into hydrogen atoms. And at that time, during the first few minutes after the Big Bang, the universe was hot enough for hydrogen atoms to fuse together to make helium. And so there's a huge amount of fusion of hydrogen to helium for the first few minutes after the Big Bang. But then after a few minutes, the universe expanded enough and cooled enough that the fusion of hydrogen and helium shut off. But even during those first few minutes after the Big Bang, that was already long enough for most of the helium that exists in the universe today to be created. So most of the helium that we have in the universe today was made during the first few minutes after the Big Bang. And then as the universe continued to expand, it continued to cool off, and eventually this light faded from the Big Bang. And we entered what's known as the cosmic dark ages. So at this point in the universe's history, the light from the Big Bang was fading, and no stars were born yet. And so the universe became relatively dark. And in theory, a universe could exist where the physics were such that stars weren't able to be created, planets were created, no heavy elements were made beyond hydrogen and helium. And in a universe of that kind, it's unlikely that life would have ever formed. But fortunately, we do live in a universe that has the right physics to make heavy elements, to make stars, planets, and eventually life. And eventually, after about 500 million years, half a billion years, gravity attracted hydrogen and helium clouds together, and these clouds of hydrogen and helium then collapsed due to gravity to make the first generation of stars. And so that ended the cosmic dark ages, this first generation of stars. So now we're going to zoom in to an individual star and see what was happening inside the first generation of stars. So the very center of a star is known as its core. And as you go deeper into a star, the temperature increases higher and higher. And so because the temperature is greatest at the center of a star, that's where you have the best chance for fusing elements. And so now what we're going to do is we're going to zoom in to the center of the star, to its core. And now we've expanded our view of the core. So we're only looking at the very center of the star. Now when a star is born, So when a star is born, it's contracting under its own weight. Gravity is causing it to pull inward. And that's what's being depicted here in a few moments. So gravity is causing the newborn star and its core to contract. And as it does that, the temperature is getting higher and higher because it's getting more compressed. And if it eventually reaches 10 million Kelvin, then hydrogen starts to fuse into helium. And so steadily over time then, the center of the star is transformed from hydrogen to helium. And then once that ends, there's no source of energy anymore to hold up the core, and so the collapse resumes once again. And eventually, it collapses so much that it reaches 100 million Kelvin, and fusion of helium into carbon and oxygen is triggered. And so now the center of the star is transformed into carbon and oxygen. And now this carbon-oxygen core starts to collapse. The temperature increases, but in the case of a star like our sun, it'll just stop at that stage. It'll never get hot enough to fuse carbon and oxygen. And this carbon-oxygen core left over from a star like the sun is known as a white dwarf. So some of you may have heard of a white dwarf before. A white dwarf is the carbon-oxygen core left over from the fusion of helium. And so eventually the outer layers of this star, a star like our sun, get expelled into space. And that takes with it some of these heavy elements that were made near the center of the star. And this nebula created by the outer layers of the star being expelled into space is called a planetary nebula. So this phenomenon we just saw, it doesn't have anything to do with planets. As you can see, there's nothing with planets going on here. But the reason it has the name of a planetary nebula is that when astronomers first saw these phenomena through telescopes, they noticed they were colorful, and they sort of reminded them of planets like Mars, for instance. And so that's how they got their name. And here are additional examples of these planetary nebulae. So this is a famous one called the Cat's Eye Nebula. This is a Hubble image of it. Here's the Eskimo Nebula. This one doesn't have a proper name, just has a catalog name. These are two other famous planetary nebula, the Helix Nebula and the Ring Nebula. And in the centers of each, you can see this little dot. So that's the carbon-oxygen core of the star, the white dwarf. And again, our sun, in billions of years, will look like this. It'll go through this stage. Now, for a more massive star than the sun, the core is able to collapse to the point that it becomes hot enough to fuse carbon and oxygen, reaches about 2 billion degrees. And now carbon and oxygen are fused into silicon. Eventually the core is transformed into silicon and then resumes its collapse, becomes compressed more and more, gets hotter and hotter, reaches about 3 billion Kelvin. Now it starts to fuse silicon. And that's transformed into iron. And now the iron core starts to collapse. It gets hotter and hotter, but it never gets hot enough to start fusing iron. And that's because you simply cannot fuse iron into a heavier element to produce energy. And so as the core starts to collapse more and more, it gets hotter and hotter, and eventually it becomes so hot that there's such intense radiation produced by this core that the gamma rays produced in this core are able to split apart the iron atoms. And we'll see that depicted in a moment here. So again, the iron core collapses, gets hotter and hotter, but it never can fuse into anything else. And so instead, it becomes so hot that the iron atoms split apart, the iron core implodes, the very center of the core is compressed to become what's called a neutron star or a black hole, and the rest of the star bounces off of the core, creating what's called a supernova explosion. And so we'll just show that once more. So again, at this point, the iron atoms are split apart. This sucks up energy. It's basically the reverse of all the other fusion reactions we've had so far. The very center of the star is compressed into a neutron star or a black hole, and the blast wave that bounces back outward tears apart the star in a supernova explosion. And this supernova explosion itself, in a split second, is able to create lots of heavy elements. So it's so powerful that it fuses the lighter elements into heavier elements. And so many of the elements in our bodies were created in supernova explosions like this billions of years ago.
Does that happen in a shock wave going out?
That fusion?
Yeah.
Right. Mm-hmm. And so this is known as a supernova remnant, this nebula that's left behind from a supernova explosion. So for instance, some of you may have heard of the Crab Nebula. The Crab Nebula is a supernova remnant. It's the remains of a supernova explosion. Now it turns out there's a second variety of supernova that involves a white dwarf. So here we have a white dwarf orbiting in a binary system with another star. And the white dwarf is close enough that it's able to pull matter off of this star onto it. And it turns out that in some situations, the white dwarf can accumulate enough matter from the other star that the white dwarf starts to implode. That triggers the fusion of carbon and oxygen throughout the white dwarf, and the whole thing blows up in a split second. And it turns out this kind of supernova also can fuse lots of heavy elements. So this is a nice summary of this process. So we started off with clouds of gas and dust on the left. Those gave birth to stars. Stars like our sun eventually become planetary nebula. The more massive stars go supernova. And in both cases, lots of heavy elements have been fused and created in the centers of these stars in the supernova explosion. And then in both cases, much of this matter, much of these heavy elements, are sent back into space to form a new nebula of gas and dust, which gives birth to a new generation of stars. And it's these heavy elements made in these stars that then later on become planets around the next generation of stars. So it's sort of ashes to ashes, dust to dust. But it turns out that those scenarios I've described so far, they don't quite explain all the heavy elements in the universe. We seem to need some other mechanisms for making elements like gold and platinum, for instance. And for quite a while, there's been this theory that, well, maybe colliding neutron stars can create lots of the gold and platinum in the universe. So again, a neutron star is a dead star created at the very center of a supernova explosion. It's much like a black hole. And sometimes you can find these neutron stars orbiting each other, and if you wait long enough, they'll spiral towards each other and merge and collide. And so for a long time, there was this theory that the merger and collision of neutron stars could create gold and platinum and other heavy elements. And it was only recently that this idea was confirmed. And here's how it was confirmed. So if you have two stars orbiting each other, they should produce ripples in space surrounding them. These are known as gravitational waves. And if the stars that are orbiting each other have very strong gravity, like two black holes or two neutron stars, these ripples should be most significant. They should be strongest in those cases. And so it's possible you might detect gravitational waves from two neutron stars that are about to merge together and collide. Now, gravitational waves can be detected in theory because these waves, these ripples in space, should cause space itself to expand and contract in opposite directions. So, for instance, if you have some object here and there are gravitational waves passing by, those waves should cause that object to expand in one direction and at the same time contract in the other direction. And this is an exaggerated illustration of this. So here's an imagination of maybe gravitational waves passing by the Earth. And so here they're causing the Earth to expand in one direction and contract in the other way. Now this is greatly exaggerated because it turns out these waves, even strong gravitational waves, only cause the length of an object to change by a small fraction of the size of an atom. So it's an incredibly small effect. And what scientists have been doing is, at 3 different sites in the United States and in Europe, they have these tunnels a few miles long where they can monitor the length of those tunnels very, very accurately. And they watch to see whether the length of those tunnels changes at all. And they can detect changes in those tunnels' lengths of only a small fraction of the size of an atom. And so last August, there was a detection by those experiments of gravitational waves produced by the merger of 2 neutron stars. Neutron stars merged, they produced a burst of gravitational waves, which were detected by those experiments. And at the same time, that merger also produced a huge explosion of gamma rays, which was detected by this satellite called Fermi. And so both the satellite detected the gamma rays, and those experiments on Earth detected the gravitational waves. And as soon as that happened, the Hubble Space Telescope and dozens of other telescopes in space and around the world started watching that place in the sky to see if they could actually witness the afterglow from the merger of those neutron stars. And this is showing a Hubble image taken over a period of a week of the fading afterglow from that merger of 2 neutron stars. And it turns out that the data collected by telescopes of that explosion confirmed that lots of heavy elements were made in that merger. And so this was the first confirmation of the idea that gold and platinum and other heavy elements can be made when you take 2 neutron stars and merge them together. And this is an artist's rendition of the two neutron stars spiraling towards each other and finally colliding. And again, this collision produced a burst of gravitational waves and also a lot of gamma rays. And that collision generated huge amounts of heavy elements. So, for instance, it's believed that this single merger probably produced enough gold to be equivalent to the size of Earth. So imagine an object the size of Earth of pure gold. That's how much was produced by this collision. And this is a nice summary of the origins, the different origins for the different elements. So for instance, in orange is color-coded the elements produced by the mergers of neutron stars. And so you can see that much of the heaviest elements are made, we think, through mergers of that kind. So for instance, here's gold. So we think most of the gold in the universe was made through the merger of two neutron stars. And we also have some of the other scenarios we discussed here, like the death of low-mass stars, the Big Bang, and so on. And so if you want to examine a diagram of this kind in more detail on your own, all you have to do is Google the origins of the elements, and then Jennifer Johnson, the astronomer who created this version of the diagram. And you can easily find this on the internet. Okay, so I'll go ahead and stop here and take any questions.
So,
Can I get an iced tea with lemon?
So the question is about the sites at which we have those gravitational wave detectors. Yeah, there are two in the United States, and there's one in Europe. It's in Italy, right?
So that's how they were triangulate, point the telescope in the right direction.
Yeah, so if you have more of these sites spread around the world, you can pinpoint more accurately the source of those waves. That's right.
I just have a side question. So, gravitational waves, the two lights are 90 degrees apart. What waves can they right down the middle? They both move the same amount and not detect all.
So are you asking, is it possible for a gravitational wave to be not detected by multiple sites?
What if he
My name is
Let's see somewhere else.
How do you spell it?
My name is Tess, but I'm
He's a better expert on that.
So I used to work with him. So yeah, if it comes down from the top, it's the most sensitive and it can detect it easily. If it came at it from the side, then it wouldn't be able to detect it because you need to measure that relative motion of those mirrors, and if they're not relatively moving, if they're not moving relative to each other, or if they're moving, well, yeah. But the other thing is though, because you have multiple detectors, even if it's coming in at one side, the curvature of the Earth is going to be such that the other one could detect it. So one of the last mergers, black hole mergers, Virgo did not detect it, the one in Italy, because it was in this blind spot.
And then are local Indians that come online?
Sorry?
Is there a way to go online?
that would be better.
Yeah. So there's going to be another one in India as well. Yeah, there will be one in India, but God knows what bureaucracy is going to push that too.
You mentioned what was going on in the core, fusing carbon, fusing silicon, and ultimately iron. Is there anything noticeable going on outside of that as you look at the star as an observer? What's different about it?
So the question is, would you notice anything different when these stars are undergoing these different fusions, right? Well, a star like our sun, in its current stage, is fusing hydrogen into helium. And then when a star is fusing helium into carbon and oxygen, it's in what's called a red giant state. And so, for instance, our next speaker will talk in more detail about the evolution of stars, especially stars like our sun. And so he'll probably talk more about that stage of evolution when stars are red giants.
You can ask me that question, yes. There were two in the back.
How simple, right at the beginning, before you form all the heavy elements, you fuse hydrogen into helium, and that reaction causes sunlight. But they always say there's a little bit of mass that's lost in that reaction. My question's very simple. If you start with hydrogen and there's certain components like Legos, building blocks of hydrogen, when that reaction is finished, are all those physical components still present at the end? If so, how do you lose mass? If physical objects like subatomic particles are still all accounted for at the end, is it the fact that the energy contained within those hydrogen atoms actually has inertial mass, and that is what is lost after they combine, or are you actually losing some of the tiny subatomic particles to account for the loss of mass?
All right, so basically, the gist of that question is that when hydrogen fuses in helium, I didn't mention this, but a small amount of the matter in the original hydrogen is transformed to energy. It's lost. And the question is, how is the state of that matter changed? Well, for one thing, when we take 4 protons, 4 hydrogen atoms, and fuse them together, we get a helium nucleus, which is 2 protons and 2 neutrons. And so basically, 2 protons have been transformed into 2 neutrons, and those neutrons weigh a little bit less. Their mass is a little bit less. And so that's one way to answer that question, is that you change 2 protons into neutrons, the neutrons weigh a little bit less, and that missing matter has been transformed into energy, into sunlight. So in other words, the light that we see from the sun, the sunlight, that sunlight used to exist in the form of matter. It used to be a part of protons, but it was transformed into energy.
Are there any stable silicon dwarfs or iron dwarfs that are not going to collapse?
So the question is, I mentioned how a white dwarf is carbon and oxygen left over from helium fusion. And that white dwarf will never fuse carbon and oxygen, or stay in that state forever. And the question is, could you have a dwarf that is made of a heavier element, like it's made of silicon or iron or something? And the answer is no, that if you start fusing elements beyond carbon and oxygen, you're destined to eventually produce either a neutron star or a black hole at the very center. You can never stop at the point of having just silicon and iron indefinitely. It's a good question.